But yeah, we are gonna just do a little bit of a board introduction today, and then we will be talking about arrays and hashing, which is our current Blind 75 topic. So if you've been following with the daily problems, we'll do a little recap on that and also dig a little deeper. We've been kind of magic waving things away a little bit, so we'll dig a little deeper into that. Uh, Sweet. Yeah, so our officers, some of us are indeed stinky. I did not write this slide, but I agree. So I'll get us going here. My name is B. Face reveal, which is crazy. Y'all have been talking about that all week. But I'm president for the club. Some info about me. I spent the summer in Seattle. I also love to steal Ivy's content, as you'll see on the next slide. I was a software engineer intern at Snap Inc. this summer. Since everyone asks this, they are headquartered in Santa Monica. I just was working in Bellevue and Seattle this summer in Washington, so that was super fun. Loved it, learned a lot. Love mechanical keyboards. We've been talking so much about keyboards in this server. I've got, I think the count right now is 14 built and also 3 cases that I've not put together yet, and I've spent way too much money. And yeah, please God, let this return offer hit, because otherwise I've been living way beyond my means for so long. Please. Favorite singular bite of food I think I've ever had is Sugarfish's Ponzu Albacore. It is so good. If you haven't tried it, highly recommend. If you like sushi. Yeah. All right, I'll pass it along to Ivy here.
Hi, I'm Ivy. I'm the vice president for Lead Club. And some things that I did over the summer is actually room with B, um, because we both had an internship in Seattle, surprisingly. Um, my internship was at Scopely. I was originally acquired by Niantic, but then they got bought out. So it's a little weird situation, but Niantic is the one that does Pokemon Go and stuff like that. So it was pretty fun. Some fun facts about me. I've watched Howl's Moving Castle over 40 times, so um, probably my favorite movie. And I really do love coffee, so if you guys have any coffee spots that you guys like near campus, that would be super great. Send a message. Yeah. And then moving on to, I don't know who's next. Someone's next.
I think it's Sid is up next here.
I'm next. Hello, I'm Sid, or some people like to call me Gato, whatever you prefer. I'm the secretary of the club, and then I basically rotted all summer and doom scrolled TikTok, while also working on some side projects. I also started playing TFT, and I'm better than Zofia at TFT. And then I'm also an energy drink addict. I love White Monsters. I'm gonna pass it to Sylvia.
Hey guys, my name is Sophia. I'm the treasurer. I did start playing TFT this summer. That was the main activity. I am died instead though. Don't listen to him. Reach Emerald in 2 months from like complete start. So other than that, I love horror movies. I don't like super boring ones. I like the ghost ones more. And I didn't just play TFT all summer. I was an AI intern at Phase 3. And I'll pass it over to David.
I'm David. I didn't really have anything interesting this summer, but I did see Hamilton for the first time, and then I proceeded to watch it another 3 times with like different groups of people. Highly recommend it if you haven't saw it or haven't seen it already. It's a masterpiece. Um, yeah. Other than that, like I love playing sports. I played football in high school, and recently I've been playing tennis and a lot of golf. So yeah.
Sweet. And that's the board. Yeah, I thought we had a transition slide here, but thanks, officers, for doing little intros here. If y'all have questions for us, we're around. Feel free to hit us up. Can we golf as team bonding? I'm not a golfer, but I'm down. Um, yeah, you guys, is this the first time we've had front-facing Duck like in content? Because we love him. Uh, if you weren't aware, the duck's name is Bill. Um, because yeah. Okay, so what we're going to be going over today, as far as content for this, welcome to. It looks like a bunch of people just hopped in. We just did a little intro on our officers. Is anyone able to hear anything? I think, because people have been like responding, so it might be you. I'm sorry to say. Great. Anyways, so I think we are going to post these slides later on, so don't worry if you've missed stuff or whatever, but we're going to talk a little bit about arrays and hashing. This is the content that we've been talking about for... Sorry, I'm like reading chat as I say this. Let me focus on what I'm going to say. This is the content we've been focusing on so far for the Blind 75. It is a really important foundation just to get used to a lot of the ins and outs of using data structures, and really these are the data structures that we'll be using for a lot of the rest of the problems. So without further ado, let's get to it. I don't want to keep y'all too long. Yeah, I think we may have not really mentioned this super broadly, but Dave Winter is our faculty advisor. He's fantastic. So if you'd like to say hi, he's in the chat right now. We love him. That's why he's got the little ducky by his name. But let's get going on content here. As always, well, if you haven't tuned into some of our live sessions, this is kind of the format of them as well. We just have people talking and explaining, and if you have questions or something to say in chat, we would love to hear it. So if there's anything you'd like to direct at me, you can @bdo or @b, and feel free to let me know you've got a question. Okay, let's take a look. So what we'll be talking about today, we will be talking about arrays, or you may know them as lists, or you may know them as array lists, or you may know them as vectors. We're going to kind of use those interchangeably today, although we'll talk about the detail a little bit. We'll talk a little bit about time complexity, hardware, static and dynamic arrays, which is kind of the thing I just mentioned. We'll also talk about hash sets and hash maps, also some time complexity stuff, and also just what hashing is. We've very much glossed over it in our sessions so far, so just wanted to get y'all a little more detail on that. So let's talk about arrays. First of all, what are they? You may, again, know them as lists, array lists, maybe vectors. They are contiguous, index-based data structures. So what does that mean? Contiguous means that the data is all stored side by side in memory. Index-based means that you can access a particular part of the array by using a number. Vastly, programming languages like to start indexes at 0, so the very first element in an array is element 0, and it counts up 1, 2, 3, 4, 5, 6 as far as you can go in the array. Arrays and lists, we say that they're mutable. Wow, so many 6 7s in chat. I'm so glad y'all loved that. Yeah, so they're mutable. And when we talk about mutability, this means that we can actually change the contents of them. So if you've got an array or a list, you can change what is in it. This is in contrast to tuples, where the data is immutable. We cannot change it. It is just what it is forever. And usually your IDE or your programming language or compiler will complain about trying to change a tuple. And ordinarily, both in the actual code and also just when we diagram or when we describe arrays, we tend to use these square brackets, as you can see, for the start digging in your butt twin array or the 6 7 array here. Square brackets tend to be how we denote those. One thing I actually glossed over here is this little bullet point that says homogeneous versus heterogeneous. What that means is that some arrays can have a mixture of data types in them, or some programming languages permit that, and others require that all of the data be the same. Python is an example of a language that permits heterogeneous arrays, like the 6 7 array here. It's got both integers and strings. Other languages, like the C languages, only permit homogeneous arrays, so it has to be the same type of data everywhere. Okay, let's keep on going here. So some common operations for arrays, and we'll dig into why they work this way in just a sec. Accessing by index, so if you want to know what is at index 0 or 2 or 5 or whatever, is what we describe as O of 1, and this means no matter how large the array is, it will take the same amount of time to get to a certain index and see what's there. Okay, we will sometimes refer to that as constant time complexity, and we're going to say that phrase a lot. What that means is, how does the speed of this operation scale with the size of the data? So if you have a really big array, does it get slower to access by index? No, it doesn't. It is actually the same amount of time. Okay, insertion and deletion. So this takes O of 1 time if it's at the end of the array. So if we need to put something on the back or take something off of the back, O of 1. If we need to insert or delete from somewhere in the middle of the array, that's O of n. And what this means for us is if you need to do that to the array, if you need to insert something or delete something in the middle, it's that the speed of that is going to scale linearly with the size of the array. So if the array gets 5 times bigger, it will take roughly 5 times as long to insert on average. Well, yeah, we'll just say to insert or to delete from the middle. Okay, searching or getting the index of a particular array. So let's say we've got an array of numbers and we want to know, hey, is the number 3 in this array? For an unsorted array, that takes O of n, which again means you've got to, or that is going to scale linearly with the size of the data. The way you can think about this is if you needed to know if something was in the array, you would just have to look through potentially all of the elements to find out, right? So since you got to do all of those things one time, it makes sense that it is a linear relationship here. We'll talk about this later, but for sorted arrays, it's going to be log n time to search your index. Hopefully, I think a lot of the folks in this meeting as well as in this server have taken data structures and algorithms already. Hopefully this feels pretty familiar, like a little bit of a review. Yeah, we'll get to binary search eventually. But this is just for straight up unsorted arrays or lists. Okay, so when do we use arrays? If we need ordering, so we need to have some concept of what is before and after. If the problem maybe specifies that things need to be in a certain order, that's going to be a great time for us to use arrays. When our data doesn't need to be changed in size, so let's say we know we have 10 elements and it's always 10 elements, or if we only need to manipulate it from the end, that could be a good reason to use an array. And I've phrased this as if you need a John data structure. What I mean by that is arrays are great as default data structures here. They're very low. You guys haven't heard that? People will say like John Elden Ring, you know, to be like the protagonist of Elden Ring. Yeah, okay. So if you need just a John data structure, a Jane data structure, this is a great pick. If you realize that you need certain superpowers, shall we say, which we'll talk about later, you may wish to change the data structure that you use, but arrays are pretty default and they're very inexpensive to create, which is of benefit to us, right? John Undertale. Great. John Cena, exactly. John Lee Club. Okay, so let's talk a little bit about these operations here, insertion and deletion. Again, assuming we're not inserting or deleting at the end, why is it O of n to do these operations? Well, here's why. So on the left here, oh, you know what? There's actually, ooh, do you guys see the laser pointer? I just found out you can do this today. Okay, so if we need to insert to the back of an array, it's actually very quick. Again, like we mentioned, arrays are contiguous, meaning the first position here is locked in place and the rest of the data always follows sequentially in memory. So these slots are sort of locked in for the array or for the list. So if we need to add something to the back, it's actually quite easy. We just reserve a little bit more space next door and then we put in the thing that we want to insert. I'm realizing one thing I missed here is telling you guys what I wanted to do here. So if we wanted to insert a 5 at the back, quite easy. We just reserve a little space, put in the 5. If you're just now learning Python, this is going to be the append. So this would be like array.append 5, for example. Okay, but here's the issue. If we need to insert something at a particular place, because we have to put everything in contiguous memory, everything's got to be neighbors to each other. Let's say we wanted to insert a 9 right here at index 1. It's not quite as easy as just putting it on the back. Instead, what we've got to do is we've got to go, hey, if we want to put something in index 1, that means everything afterwards has to get shifted over and we can't lose the data, right? So we would start by saying, let's reserve ourselves a little bit of space, move the 5 over here, move the 0 over there, move the 2 over here, move the 1 over there, move the 4 over here. And now that we've finally made space at the index that we wanted, we can put in this 9. Okay, so intuitively, hopefully this feels intuitive, right? If you need to put something in the middle, you got to shift everything afterwards back by 1, right? So if we are going to consistently need to put things into a specific place of the array, exactly, it's sort of a PETA. Which means if this is something we're doing often, maybe we should think about a different data structure, right? So this is a weakness of arrays. If we constantly need to insert to the middle, this is something we want to avoid. Removal is sort of the same idea. If we need to remove from the back, it's quite easy. We just say, hey, the last element is not allowed anymore. It's not part of the array. Chop it off, and we're good. But if we need to remove from a particular place in the middle, let's say we wanted to remove the element at index n equals 3, first we have to go to that index, right? And we got to say, well, everything after this has to get shifted forward, right? So we would say, I'm going to get rid of this 1, the 2 will move forward, the 0 will move forward, and then finally, when we've moved everything afterwards forward, we're set to go, right? So the closer we are to the back, the better it is to do one of these kinds of operations. When we talk about time complexity, we usually want to refer to what the worst case would be, or really in practice, we tend to think about the average case. What is going to happen most of the time? My nerds, there's actually a little bit of a better syntax for that. If you want to talk about the average case, we actually tend to say theta of n. That means most of the time, this is going to be the behavior. I'm saying for the people who are nerds who want to know about the weird terminology. Yes, for the nerds in the crowd, which is not all of you, but for the nerds, average case is theta, worst case is O, and actually best case is omega. So now you know. All right. Okay, any questions so far? I've kind of like been half looking at chat. 259 new messages is crazy, you guys. Okay. I'm gonna say no questions. But if you have questions, ping me, because it's too many messages in here, okay? Okay. Great. Okay, so a little bit more information about arrays. Hardware, I know we're comp sci people, we don't need to talk about hardware a ton, but as we all know, memory is just boxes with numbers, right? Caches just so happen to also pretty much just be boxes with numbers, and caches really love when we are accessing contiguous memory. So when caches store data from random access memory, they tend to store more than just one piece of data. It tends to be several pieces of data in a row, which means if we can look at, or if we need all of those pieces of data, we're in a great position. Computers love contiguous memory. It can really boost performance. I've included a little GIF of Gojo saying how I imagine it feels to get a cache hit as a computer. And I just know it hits. Like, I know it hits. All right. Last piece of information about arrays. So we've got static and dynamic arrays. Technically, what static and dynamic mean, the distinction is that static things are set at compile time. So while you're writing the code, you already know what the array will look like. Dynamic means at runtime, you find out what the array will look like. Static tends to perform better, but it has stricter requirements. Namely, you have to know what the array is supposed to look like when you start. Okay, some languages actually have both. So you have the option of using, for example, a standard array that is statically defined versus something like vector from the standard library. Others don't, so like Python doesn't really let you pick. You just use list, and that's what it is. Small piece of detail for those of us who really love talking about performance and things like that. Vector resizing can sometimes be optimized. So if you know you'll need a variable amount of data, but you have some idea of what the size of the data is, as you resize vectors, it's a little bit more expensive to just like resize and resize and resize, and your data is growing and growing and growing. So if you know it's going to be 100 or 200 elements or 500 elements, you can say, let's go ahead and reserve lots of space, and then we can just use it as we go instead of having to resize. So, tiny detail. All right, well, we're about to move on to sets and maps. Any questions about arrays before we keep going? You hate arrays? Why do you hate arrays? Arrays are great. Will the slides be posted? Yeah, we'll post them somewhere. Aw, thanks, Dave. Okay, so sets and maps. What exactly are these? So both of these data structures use hashing to store unique keys. We'll talk about that in a little bit more detail in a sec. But sets and maps are under this category of hashing or hash data structures. So if you're wondering why we keep saying hashing, we're talking about these two data structures here. Sets are just to store actual pieces of data. So we could say maybe sets store the keys, whereas maps pair up those keys with values. Okay. So up here, ooh, laser. Up here we've got an example of a map, or you may call it a dictionary in your language. Exactly. So dictionaries in Python, maps and dictionaries, same thing. Sets are their own thing, so separate things here. This up here would be an example of a map or a dictionary, or in JavaScript they actually just call them objects. This could be an example of a set where it's just unique pieces of data. One really important thing that I actually also called sets in Python. So one really important thing that I kind of glossed over here, these store unique keys, okay? So we cannot have duplicate keys in a map, nor can we have duplicate elements in a set. If we encounter a duplicate and we try to throw it into a set that already has it, it will just not get added in because it's already there. So we only ever have one copy of the items in a set, one copy of the keys in a map. Okay, so speaking of these keys, they have to be hashable. Hashable. That's why I've got the hash brown. Okay, anyways, they have to be hashable, which generally just means we can't use stuff that changes on the fly. So for example, like you can't use a list, a dynamically generated list, because if that stuff changes, where's the key now, right? So we'll talk a little bit more about that in a sec. Again, in the code, as well as just generally when we diagram, we use curly braces for both of these types. And I should have mentioned, but the colon also pairs together keys and values in the map. All right. It does look like a chicken nugget, doesn't it? Okay. Someone said proof of what? Oh, for the fart? Okay, we're moving on. Okay, little bit of analogy time here. Are the slides being uploaded? Yes. And Ivy, great point. In C++, we actually have both unordered maps and just the standard map. In terms of hash sets, if you want the performance that we're going to talk about right now, that's going to be the unordered map in C++. Standard map is ordered, and that comes with some performance trade-offs. So if you want to use it the way we're using it, we're talking about unordered map. We're actually going to talk about hashing in a sec, so if you're confused about what I mean by hashing, we'll talk about it in a moment. So here's a little analogy for sets. So imagine we're at Elite Club GBM and we're taking attendance, right? You've got a folder with dividers like these ones. You've got a tab for each letter of the alphabet, right? And as people attend, we're going to write their names down in one of these or behind one of these dividers, right? Now, real nice benefit of having dividers like these. Why am I caressing that in? Okay, I'm sorry, I need to not look at chat. If someone asks you something like, hey, have we gotten any S names yet? Is S present in the set, so to speak? It takes no time at all. It doesn't matter how many letters there are. You can go straight to S, open it up, and see if there's anything in there, right? Now, this isn't like a perfect analogy, and that's because there are like only 26 letters, right? So at some point, the way that names work is we're going to see another name that belongs behind that letter, right? We're going to go into more detail about that in a sec. But in short, the nice thing about this is we can check if we've encountered a key, if we can check if we encountered an element without concern for how long the list is, right? Now, by contrast, imagine if we just wrote down all of the names. To check if we have seen one of the names before or one of the letters before, we've got to look through every single one of the letters till we get to maybe the thing that we've seen, right? This is actually a great question. Would they be counted as one? We're actually going to cover this in just a second, so hold that question because we will get back to it. So as far as maps go, this is literally the exact same thing, but this time we also write their phone number down next to their name, or maybe you want to store a few things next to their name, like an array of data. So these values can be data structures themselves. So, Raul, great question. What if two people have the same name, like John Smith? Wouldn't they be counted as one? This point right here, which we'll actually start with because somebody asked this question, that scenario is called a collision, okay? And it's totally possible for that to happen. What data structures are doing, or what this data structure is doing behind the scene, is if a collision occurs, they have some alternative data structure to say, okay, here's a couple things that are all being stored in the same place. And then we would have to look through those things. So let's talk about this though, because earlier somebody asked, hey, what is hashing? What do you mean by a hash map? What do you mean by hashable? All hashing is taking some input and producing a predictable and unique output. So for example, if someone's name is Dave, the hash function might just take the first letter of their first name. That is technically a hash function. Anybody who's got a name, you can take the first letter of their first name. Now, is that a good hash function? Probably not, and one of the reasons for that, yeah, exactly. So Dave has actually described what a good hash does, but one reason why that's a bad hash is because it produces a lot of collisions, right? We're gonna have a lot of people whose names start with the same letters. Now, thankfully, we don't have to worry about that too much. You're not usually going to be writing your own hash functions. Somebody has done it for you and it works, and we can accept that it works. So generally what should happen though is you throw in a piece of data, and whatever the hash function is spits out some crazy string with tons of randomness to it. And ideally each input is very different from each input's hash is what I should say, is very different from the next input's hash. And this makes it very easy, hopefully, for us to take an input, put it into the hash function and go, have we seen that hash before? Because we know exactly where to look for it. Okay. So why are lists not hashable then? Because if we change the data, the hash is going to be different as well, right? Okay. So yeah, so to address the questions, what's hashing? It's just figuring out a good way to find if we have seen this thing before, and specifically the way we do that is taking the input and producing its own lovely unique output. Okay. Great. More questions at all? Anybody? Anybody? I'm going to keep going. Oh. Discord has all of you guys' names like truncated right now, so I don't even know who's typing. Could be anybody. Okay. Wait, what? It turns out it was both of you, all three of you. Okay, we'll keep going. So here's something cool. For common operations on sets and maps, insertion and deletion are both O of 1. We can compute the hash regardless of the amount of data we've put into the hash map or the hash set so far. And also deleting is very easy for us to do because we can find the hash and then just say, hey, by the way, that's not valid data anymore, or the thing that we're looking for isn't valid. What's the trade-off? The trade-off is that there's no ordering. Well, there's a few trade-offs. There's no ordering, so if you needed to sort the data, for example, you couldn't do that with just the nature of a set or a map. You would need to produce a list out of it or something like that. I should say, before we actually get to that, searching or identifying if an element is a member of a hash set or a hash map is also O of 1, because again, we compute the hash and we just see, hey, is the thing at that location or is it not? Yeah, so to speak, is it behind that divider tab or is it not? So the trade-off, one is that we can't order the data anymore. It's not 100% true, but we'll say that it's true for now. Let me think, other trade-offs? Not a ton, to be honest. We use these a lot. Well, I guess here's the other big trade-off, is that there's a lot of overhead to maintaining these things. So if we're working with tons of data, it's in our interest to do some expensive things up front, and as a benefit, we get this very good time complexity. If we're only managing a couple of pieces of data, it's not worth all of the computational effort to make a map, to make and maintain the hash table for the map, and do all of these other things. So yeah, the other thing is if we need, I guess, yeah, S-tier data structure. Exactly, we love hashing. Okay, sorry, I'm gonna take a breather. Common use cases for hashing data structures, so sets and maps. If we want to detect duplicates, so if we're asking the question, hey, have we seen this before? Or if we need to deduplicate data, so we want to get rid of the duplicates, this is a great use case for these. If you need to quickly find data associated with certain keys or elements, that would be a great use for maps. So for example, if you need the frequency of a certain element in an array, you can create a map and very quickly look that up. Or, if there's some other calculation we're making that's very expensive that we need to record that's associated with a certain key. And again, like we just answered in the last question, if our data is sufficiently large, it's worth using these. If it's really small data, creating these data structures often isn't really worth it. Okay. Oh, wow, is that? Okay, this is actually pretty, I think this is our second to last slide here. So just some relevant problems now that you've learned a little bit about arrays, hashing. First of all of the ones we've done so far have been related in some way to arrays and hashing. These are some other ones. I think this guy is one we've covered already, which we'll talk about a little bit right now. This guy, I think, is later on in the Blind 75, so we'll see it at some point. This one is actually one that is not, I believe, in the Blind 75, so it might be a good one to tackle on your own. Notice I haven't actually told you whether these guys need arrays, sets, or maps. So which one is which? I don't know. Maybe you should try the problem and find out. But I think doing these three problems would be a great way. I think doing these three problems would be a great way to explore a little bit what the trade-offs are. You can do a little bit of your own consideration on, well, which one should it be, right? Let's actually look at, well, I think I'm showing you guys this display right now. So, ooh, I don't know what's on the stream right now, but let's look at this problem. Can you guys still see? Can you guys still see that? Okay, great. Let's just look at the problem real quick and we'll just discuss a little bit about how we know which data structure is appropriate here. The prompt for the problem is given an integer array nums and an integer k. We want to return the k most frequent elements and we can return the answer in any order. So we're given some data like this, 1, 1, 1, 2, 2, 3. So if we needed to figure out which elements were most frequent, or the k most frequent of them here, an array is not super appropriate because it doesn't give us an efficient way of knowing as we look through the elements if we've seen an element before, right? Does my mouse show up here? Is the mouse on the screen? Okay, great. So, for example, we look at this first guy. Have we seen a 1 before? I don't know. Look through all the elements that we've looked at so far. Okay, we get to the next one. Have we seen a 1 before? Okay, yeah, we have. We check it here. But every time we look at one of these, we have to potentially comb through all of the previous elements. So we get here, hey, have we seen a 2 before? Well, that's not a 2, that's not a 2, that's not a 2. Have we seen a 2 before? That's not a 2, that's not a 2, that's not a 2. And in the worst case, imagine if this was, well, I've got a solution here. But in the worst case, imagine that this was something like 1, 2, 3, 4, 5, 6, and so on. Every time we want to know if we've seen an element before, we have to look through all of the previous elements, right? We get to the 9 and we have to say, is that a 9? 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 This is very inefficient, right? Surely there's a better way for us to find out if we've seen a 9 before. Okay, so you might think, oh, you know what? We talked about hashing. We talked about sets before. Maybe we could do that. So if we create a set out of this, we can very quickly figure out, again, if we're looking at 9, hey, have we seen a 9 before? Immediately we can say, no, we haven't seen a 9 before, right? But here's the flip side of it. Let's say we do have duplicate data. Like we've got 1, 1, 1, 2, 2, 3. Yikes. If we just produce a set, maybe we got 1 and 2 in here. Well, maybe we've just got 1 in here so far. When we get to this element, we can ask the set, hey, have we seen a 1 before? And we get the answer yes. But we have no idea how many times we've seen the 1 before, right? So the set's not useful to us because we still have to go back and count. How many times have we seen 1 in order to know the frequency overall, right? And this leads us to, hopefully, we can see this is kind of the ideal data structure for us here is a map. As we go, so I'll actually do this step by step. The first element we say, hey, we've seen 1 at this point 1 time. Next time we consult the map, we ask, hey, have we seen 1 yet? Yeah, we've seen 1, so we'll increment the count for it. So I'll say this is like element to frequency. Okay, for the third one, we ask, have we seen 1 before? We sure have, so we increment the count of it. When we get to the 2, we say, hey, you know what, have we seen 2? No, we haven't, so we'll go ahead and set its count to 1. Next time we say, have we seen 2? We sure have, so let's increment its count by 1. And then finally we get to the 3. Have we seen 3? No. So we can go ahead and set its count to 1. Okay, so there's more to this problem, but in short, this is, I think, a great contrast to why each of the data structures works the best for a particular problem. In this case, the map is perfect because we have to do a lot of searching for the presence of elements. We need to know an additional piece of information about the elements, which means the set isn't appropriate, and this leads us to the map. Okay, that was a lot of talking. I think that's all I've got for you guys. The last slide, I think, is just, yeah, our sign in again. How is dict different from map? Dictionaries and maps generally refer to the same things. I actually just realized I saw in the chat earlier someone asked, are ordered maps trees? C++ has them implemented as trees, so now you know. But we've been talking about unordered maps. So how are dicts different from maps? They're the same thing. They're just two different words to refer to the same type of data structure. If you are a JavaScript coder, you also may see these referred to as objects. In short, we're talking about key value pairs here that are hashed, where the keys are hashed. Lots of different names for them, though. Great. Will this meeting be recorded? I'm recording it right now. I don't know if the recording is working. I hope it is. If it is, we will post it soon. The slides will definitely be posted. The recording hopefully is posted. This is the same QR code as earlier, so if you already signed in, you don't need to do it again. Again, we would just love to know who's here / how many people are here so we can plan for future GBMs. Great. Thanks for being here, y'all. Any questions for me or the board? Do I wear wigs? Maybe one day. Do you get a cookie? Are you in 350 right now? There's going to be cookies at our in-person meetups for Engineering 350. I promise you that. I didn't say you were going to bring the cookies, Dave. I just said there would be cookies. Will GBMs always be online? This one is because, well, let me say this lightly. ASI hates new student clubs. Just kidding. There's a lot of construction going on. It's tough to get a space on campus right now, as well as we're a new club, so we're still working on some registration documents. But we will eventually have in-person GBMs, and we're going to do our best to also stream those to Discord in case you can't make it physically. So hopefully coming to a better medium soon. Any other questions? Any other questions? Ooh. Well, if you haven't done an arrays and hashing problem, there's 6 of them. Post it. Tackle one. Now you know it's arrays and hashing. You just got to figure out which data structure you're supposed to use. Did I just belch? Do you want me to? No, that was just vocal fry. That was just, usually the journey is the part you remember anyways. That was that. Okay, great. Thanks so much for tuning in, guys. I'm gonna call it there. Speak now or forever hold your peace. Maybe we'll do the Wiccan battle cry at the in-person GBM. Okay, I'm calling it there. Good night, everybody. I will see ya maybe for the live Blind 75 session tomorrow night. Good night.